part in blokkopolymer film. This work was done by my PhD student, and the Korean group, and the co-work with the UMass group. So there are a lot of different strategies to make nanosize patterns. So usually lithography is widely used. So somebody also used nanoparticles. Also anodization of aluminum. So this is also useful. But in blokkopolymer case, the size is about 20 to 50 or 60 nanometers. But sometimes we want to decrease size, or sometimes we need to increase size. But we cannot decrease the blokkopolymer size. So today I'm just talk on the perpendicularly oriented hexa nanodomain. Okay, my voice is just so small. Okay, then I think my voice. Okay, then there are usually there are three different research trends. One is the control the pore size or nanodomain size. The other one is L by D equation control. Finally, long range ordering already. Professor Park already talked about this one. So zone defining or zone defining. Today I'm really talk on the control the pore size. So in order to control pore size, we use the polymer mixture. Then the other one is we for the first time use the ozonization. So if we use this ozone, then some blocks can be costly, then volume should shrink. So this is the first time T.P.Russell groups reported that if we change the substrate by random copolymer, or we call neutral surface, then cylindrical domains oriented perpendicularly to substrate. Of course, about 5 years ago, there are a lot of defects here, although all the cylinders are oriented perpendicularly to the substrate. But usually for making some storage device, first we are oriented vertically, then we remove by some photo degradation or UV degradation, then we can get a hole, then we deposit metals, then finally we remove the matrix. So T.P.Russell's group already reported for generation of a nanowire. So here the diameter is about 20 nanometers, thickness is 500 nanometers. But the problem is that of course this is just our imagination. So if we have some nanowire here, then the distance between two nanowires is too close, then there are some interference happens. So in order to increase the interdomain size, but however, then we cannot increase the density. So the best way to increase the interdomain spacing without sacrificing the density, then we must choose the smaller size of the nano size. So how do we get the smaller nano size of pores? So first we think that if we put into a homopolymer here, then homopolymer is located at the center of the block, then we can eliminate homopolymer by extraction, then we can get some nano hole. Of course, this nano hole is much smaller than original block or polymer. Later I show the cross linking. So, but however, it's very difficult. How do you know the homopolymer is located in the center of the block? So that is a very difficult question. So there are two general categories. One is the localized solubilization. The other one is the homopolymer mixed together. Then in that case, that is almost useless for our purpose. So the best way is the homopolymer should be located at the center of the line. But still, we are trying to find where the homopolymer, but so far we do not get the exact position. But however, if we put into this is a PS-PMMA block of polymer, 30% of PMMA block, so PMMA block becomes the cylinder. Also, cylinder is oriented to substrate. If we put into a homopolymer, then domain size is increased. Then where is the homopolymer? So inside here, there should be a homopolymer. So in that case, we just put in, use the acetic acid water solvent, then PMMA homopolymer can be extracted. But that it is not easy to find the holes touched to silicon wafers. So in order to compound the holes or smooth away the bottom of the film, then we just use the simple techniques. So here we just first evaporate silicon oxide about 100 nanometer. Then the HF remove the silicon oxide. So in the HF solution, then films is flip off. In that case, the bottom is this is the top surface. Then if we flip off, then this is the bottom side. So we can measure the AFM image of top and bottom. So sometimes if we are very lucky, then we can get some channel connect to top and the bottom. And if channel and if we can see the hole on the bottom, then the hole is touched the silicon wafers. So this is after we remove this is the top surface and the bottom surface, which is the same size. Of course, if we use the UV etching, then UV remove the whole PMMA block. So this is only the homopolymer PMMA location. This is the whole block. So this is about 6 nanometer. This is about 22 nanometers. So we can generate about the 6, sometimes 8 nanometers. Also, sometimes we see the channel in this way. So we can see the hole is connected to the bottom of the films. So that is a very beautiful work. But the problem is this hole is not stable to thermally. Once the film is exposed at a high temperature, then PMMA block chain in the PMMA block can penetrate the hole, then hole suddenly disappear. Then how do we, of course, this one is, of course, we know that this is the cobalt electrode deposition. So if we electrode deposit by cobalt, then the size is about 6 or 7 nanometers. So this is much smaller than previously condenses. Condenses is the size is about 25 nanometers. So in order to have some thermally stable nanoholes, we introduce some cross-linking techniques. So what is the cross-linking techniques? This is the PS and the PMMA. So if we use the ozone treatment, polystyrene can be cross-linked, but the PMMA cannot be. So if the polymers is cross-linked, then volume is shrink. But this PMMA is not shrink. Then there are some mismatches. So in order to put this boundary to connect to connectivity, so the best way to reduce volume is decrease the height, but this one is of course volume is reduced, but this one does not reduce the height. Then the best way is PMMA block should move this way. So in the center of the PMMA becomes the hole, nano holes. So we can simply predict the nano hole size. This is not much easy, not much difficult. So we can calculate the nano hole size. This is the original block radius. This is the final hole size. That is only dependent on the thickness ratio decrease upon the cross link. So this is if we are ozone exposed, then PMMA does not cross link, so almost the thickness is the same. But in homopolymer case, the thickness is decreased. For black polymer, almost half of between this one. So we can predict the hole size. So if we increase this ozone time, then first the hole size is increased. Then about after 30 minutes, then hole becomes the hole size becomes the steady values. So this one is measured by TM. So actually the prediction and the actual measured value is so close. So this is actually we saw the TM pictures. Of course, 10 minutes we only see 2 or 3 nanometers, so small. But if you see 30 minutes or 60 minutes, you can see about 6 or 7 nanometers here. So this one is another we use the out of focus technique of TM. Then the hole becomes very high. So around gray area is the block of the PMMA block. So here we can generate even 2 or 3 nanometers. Although the we are not quite sure, but still we see 2 or 3 nanometers. But we did not succeed to make the nanowire. Here we can already make the nanowires. Then I moved one more. Then I used the combination of ozone and mixtures. So previously I used only the PMMA, but at that time I did not use ozone. But if I use ozone, then PMMA cross-link. Then if, even though there are holes, that holes is very stable because this is already cross-linked. Then PMMA chain cannot move to hole. So that hole is a very stable hole. So this one is without adding the homopolymer. Already you see about 6 nanometers. But if we put into a 1.5% of homopolymer, then nanohole size increase, then 9%, 20% increase. Also, the one clue is that if these rings should be very circles, means homopolymers or holes will be located at the center of the block. So in that case also we measured we predicted the hole size using this one. Of course here there are 2 factors to generate the hole. One is the cross-link, the other one is the homopolymer. So we can calculate the homopolymer and the cross-link. Then finally we got the hole size. So in cross-link case, this just gives us a small amount of area because the cross-link does not affect the diameter because the cross-link cannot, ozone cannot cross-link PMMA. So this is just due to TS block. But for homopolymer areas increase with increase the amount of homopolymers. So the final area is here. So this is the prediction. We got the TM data. So this is very nice. So in that case, we can control to a 5 or 15 nanometer hole size. So I just introduce two more slides. Of course, if we have holes, then we can make the quantum dot. Of course, a lot of different techniques is used to make the quantum dot, but for our case, just we can make the hole, and then we use the silicon chemistry, and this shows the silicon nanopost. But about months ago, Russell's groups also are used just to evaporate, because instead of using the silicon chemistry, evaporation is a very simple job, but very, very difficult to fill out the nano holes. But they succeeded. First, they put into a chromium evaporator. So because they want to make the gold nanoparticles, but gold cannot be contact with silicon. So they first evaporate chrome, then they evaporate gold again, so they can get a very nice quantum dot. So that is a very interesting technique. So right now we are thinking about this one is just about 10 nanometers. How about this is about 100 nanometers? Is it possible to evaporate or penetrate all the metal evaporation? So if we can develop that technique, that would be very good jobs. So I just summarize my holes. Nano hole size is controlled, also predict. Even 3 or 4 nanometers, we can get it. So if we can get it this small nano size wire, then it gives a lot of applications. Also, we change the level size and the domain size. But unfortunately, I did not discuss height controls. Also, metal or inorganic materials are easily fit to nanopods. Of course, there are some long-range single crystal like this is maybe a future work. Of course, as I told you, Russell groups got some perpendicular hexacycline. Of course, the Kramer groups get a spherical nanodomain. Looks like single crystal using the cooperative texture. So that is still some very good subject. But also we think this is also very interesting subject. Okay.